So let's come to the choice of the operators we use. So let's talk about interpolating operators. Sorry, I'm misspelling. So there's enormous freedom in what we choose for these operators. Um, and before we try and build them, let's look at the kind of features we see in correlation functions. And this is actually something that is fairly specific to the theory we're interested in. So I'm going to define the effective mass function, and with t, which is log of c of t plus 1 over c of t. And here I'm just thinking about a single correlation function again for a moment. If you're in the large time region where only one exponential is dominating this will go to a constant. And that constant would be the energy of the state. And again, here I'm taking t goes to infinity and a single correlation function. So what does this look like when we try and actually calculate it in lattice QCD? So let me draw a sketch of what we see. So as a function of time, here is m of t. Okay, so we evaluate stochastically on a discrete set of points. So let me draw some points. And this is kind of what we see. Um, so there's really three regions to this behavior. So there's a region here. There's a region kind of that's doing this. And then there's this final region here. Okay, so let's talk about these. And here again, we're assuming t is infinite. And you can see that in early times, there is strong t dependence. And that indicates that many exponentials, or multiple, are contributing significantly. Okay. There's a region where m of t is independent of t within uncertainties. And the uncertainties grow as t increases. And then finally, there's a region where there's very large statistical fluctuation. And the behavior is likely non-Gaussian. So the choice of interpolating operator strongly affects these regions. Um, and really, the way in which it does this defines the goals in constructing interpolating operators. So we want to extract the we want to optimize for the extraction of the energy eigenvalues. And we want to do this in two ways. So firstly, if we could get rid of this excited state region at the start, where there's more than one state contributing, then we could make use of the very precise numerical results in that region. So our goal is to reduce the effect of high energy states. And if we could reduce the statistical fluctuations in region 2 and maybe region 3, then we would also be able to better extract the signal. So we've sort of talked about the first of these. So reducing excited states that's achieved by finding an operator that has large overlaps onto a single state. So in the GEVP approach, we constructed the operator this operator chi A, which was sum over sum over the operators that we wrote down, and this one had that. Oops. Dominated by the state A and had small contamination. So what can we say about the statistical noise? Okay, so this comes from, of course, Monte Carlo sampling. So given a set of configurations of the fields of the theory, which I'll just call phi. So the index is just labeling which configuration. Well, we estimate the expectation value by taking the mean, and this is an estimate of the value of the path interval. Um, so C bar of t, which is so this curly C is the correlation function whose expectation is the thing we're after. And this is the an unbiased estimator through the mean. Okay. And this has variance which is the square of the difference between the samples and the mean. And you can, of course, write this as an expectation value. It's given as expectation value of mod C of t squared minus the mod of the expectation value of C of t squared. So if C of t, which is just the operators, so this is like chi of t, chi twiddle dagger of 0, then we can ask, what is this quantity here? And in fact, it's a perfectly good correlation function. And you do exactly what it says. You take this object and its dagger and put them in your expectation value. Okay. And I would note it's kind of important. This expectation value is over the sampled fields. So in QCD in particular, this is an expectation value over the gluon fields. And that's after the fermionic integration has been done. So it's an expression written in terms of propagators. But nonetheless, this thing is a perfectly good correlation function. And as I take t to infinity, it's going to decay like a sum of exponentials. And at large t, it's going to be dominated by 1. Where this E naught twiddle is the lowest energy state with the quantum numbers of mod chi squared. And by that I mean that that 0 mod chi squared n twiddle is not equal to 0. Okay. So because of this, we've got the mean and the variance. We can look at the ratio of the signal to noise. Which is really a characterization of the quality of our data. This is given by this, and as t goes to infinity, well, the numerator goes like e to the minus e naught t, there's some number here, and the denominator goes like e to the minus e naught twiddle t divided by 2 because we've taken the square root. And so this is equal to number times e to the minus e naught minus e naught twiddle over 2t. And this is called Parisi-Lepage scaling. And if e naught twiddle is less than 2 e naught, then the signal quality degrades, which is what we see in most cases. And this generally is the case. Okay, so we now come to an exercise, and let me add another page and move some of these off. Come to an exercise here. So let's take C of t to be a correlation function built with any of the following sets of quantum numbers. And the question is, what state would you expect to set the scale of this E naught twiddle that governs the fall off of the variance? So look at a pion at 0 momentum, a pion at non-zero momentum, proton at 0 momentum, a 0 plus plus glue ball, a scalar glue ball, and helium-4. Okay. So we can think about what states are going to have the smallest noise. Oh, sorry, what interpolating operators? Have a small variance are going to be operators that so we'll call them gamma, such that mod gamma squared has small overlaps onto states with energies E twiddle n less than or equal to 2 E naught. So if you made the overlaps onto those states that are less than that threshold, then you would see that the noise is essentially constant. And in fact, you can phrase this problem in a algebraic way similar to the generalized eigenvalue problem. Okay, so more concretely, how do we choose interpolating operators? We know what the goals are. Whoops, uh, let me add another page. Good. And I think this is really a bit of an art. And there is no principled way to do this systematically. But let's proceed anyway. Okay, so step one is we want to define the quantum numbers that we're interested in. And these are really the things that are preserved by QCD. So total momentum, the cubic group transformation, assuming we're using a hypercubic lattice, the cubic group transformation properties, or if we've got a non-zero momentum, the little group transformation properties. Um, so what representation does your state transform under? Um, and also what role of the representation? And these are the lattice analogs of the J squared and JZ. The angular momentum quantum numbers. Okay. You can look at parity, charge conjugation, baryon number, isospin, so I squared and IZ, strangeness, charmness, whatever. And you could, for example, think about SU, the SU3 flavor representation. Okay. So for quantum numbers that are single hadrons, we can start by using quark model wave functions. For example, if I take the K plus meson, chi K plus of X, bu bar A of X, gamma 5, S of SA of X, where the A indices are color and the spin indices are contracted here. Or for the proton, so this is a little bit more tricky. So the color indices are contracted with an epsilon tensor to give you a color singlet. And this combination here makes a spin 0 diquark. So all of the spin indices with the U and the D here are contracted with the C gamma 5 matrix. And of course, C is I gamma 0, gamma 2. And the spin of the proton is carried by this third quark here. Okay, so let me grab an exercise. Copy. Cut. Paste it here. Okay, so I want you to take these ideas and build interpolating operators for octet and decouplet baryons, and for the sextet and antitriplet singly bottom baryons. And you may need to look up what those are. Okay, so this creates an object at a single point. And of course, a single point is really not what a proton looks like. For example, we think that's something that has a size around a Fermi. So instead of building this from entirely local operators, we can use smeared out versions of the quark fields. With a smearing radius of order 1 Fermi, the size of the proton. So for quantum numbers that we can't build quark model wave functions for, we can make use of displaced fields. Operators that are not at a single point. So, for example, if we take the pi plus, and so this is some combination of a quark field at one site and a quark field at one side over, connected by a gluon link to maintain gauge invariance. You can also add any number of gauge invariant gluonic contributions. certainly something you're free to do. And then we can also consider operators built from multiple color singlet components. So chi for the proton. So we'll take the thing we had before. But then I'm going to multiply it by something that looks like a pion. That's a perfectly good interpolating operator. And in this case, it's often sensible to try and do this in momentum space. Where we might, for example, write the following. Let me write it as following. Looks like I just write that as chi alpha plot of x and y. And so this is something determined by two momenta. Of course, the only quantum number is the total momentum. But the relative momentum is, of course, in, is not a quantum number because it's been modified by interactions. Okay, so we get to another question. I guess I can fit that. I'm just going to try and neaten things up a little bit. There's a bit more space. So our problem is let's construct an operator that's a momentum projected pi plus. Okay. And I want to build a correlation function built from a source that is two of these and a sink that is the decker of two of these. Okay, labeled by momentum P1, P2, P3, P4. So one of the issues that comes up with these multi-color singlet component objects is the computational costs go up. And a question to ask is, what is going to be the scaling with the spatial volume of this particular correlation function? Okay. So that's kind of some rules you can think about when constructing operators. Some things to note. Um, so if we consider a correlation function chi twiddle that contains fermions, then the involves evaluating all the Wick contractions that arise from the fermion integration. And so it can get expensive. And this really limits how complicated an operator you consider. So for an example, an interpolating operator for the proton that look like a proton and then 23 pions, may be a perfectly good interpolating operator, but the number of Wick contractions that you need to evaluate that's going to be very large and challenging to compute. I also want to add one cautionary remark. Yeah, and that really is that there's a tendency for us to do things that are obvious and that we know how to do and we can afford to do. And I think it's fairly unlikely that the actual eigenstates of the theory fall into the class of these particular things. So we're really never going to directly access the eigenstates. Um, and so, yeah, the cautionary remark is really that spectroscopy being variational is going to give us upper bounds no matter what we choose. But trying to get more out of it than that is uh, something you really want to be careful about. So that brings me to the following. So here's a cautionary tale from the HadSpec collaboration, who have worked on hadron spectroscopy for many years. And this is for the rho meson. Okay, and this is an I = 1 resonance in pi scattering. And the reference for this is BRD 92094502 2015. Okay, so they considered spectroscopy and their operators they chose are the following. So local quark bilinears, so things that were with various different gamma structures and displacements. And so they took 26 of these. Then they also looked at pi-pi-like operators. So sum over x, either the I p dot x psi bar x gamma 5 x. And also k0, oh, no, kk bar. So either k plus k minus or k0, k0 bar. And these are very similar, but we use u bar gamma 5 s s bar gamma 5 u. And what we'll see is the spectral bounds depend strongly on which operators we use. Okay, so this is a figure from the paper. And it contains the spectrum that you get when you do various different choices of operators. So the first column is the spectrum. So really, these little bands here are the extracted energies when you use all of the operators. The second column is when you exclude the kk bar operator. Third column is when you exclude all of the kk bar and pi-pi operators. And I should have said there were 3 of these and 1 of this. Okay. And finally, the last column is you get this when you only look at the meson-meson type operators. As you can see, the spectrum shifts significantly when you take these different choices. If you interpret these as the energies, then you can have problems. For example, if you take the all operator set as the ground truth, then this determination of an energy here is just wrong. If you interpret these as bounds, well, this is indeed a bound on this state, and this is indeed a bound on this state here. So interpreting this correctly as a variational bound, everything is fine, but you can see that some of them give much better bounds, for example, this, than this. Okay. Great. Okay. So I want to ask a question about this before we move on. Okay, so what are some other operators you might consider adding to this set? And what do you think they will do to the picture that we see? And how sure are you of the answer to this question? All right, so let's move on to one final topic. And that is Wick contractions. And as I mentioned, if you have multiple color singlet contributions to your operator, then the number of Wick contractions can become very large. So naively, for a two-point function, there are going to be we'll just call it nu factorial, nd factorial, ns factorial with contractions, where each of these is the number of quark fields of flavor I in chi twiddle dagger. Firstly, I would note that symmetries reduce this. So for example, if I have a interpolating operator that is two protons, then interchange of those protons just gives me a minus sign, and that will reduce things. Okay, so let me come to another question. And this may be close to the last question. Cut. Yeah. Okay, so the pion is a spin zero isotriplet state. So there's pi plus, pi minus, and pi zero, as I'm sure you know. So what are the allowed isospins of a two-pion system? And for each total isospin, construct the state of the largest IZ. Now, using the simplest possible interpolating operator for each pion, draw diagrams corresponding to all topologies of Wick contractions for the correlators that you build from these operators. Okay? And as a challenge, also do this for three pions. Okay. So that is the generic statement, is that this is a factorially difficult problem. But there are ways in which you can make things behave a little bit better. And different computational strategies can reduce the costs. And so as an extreme example of this, by exploiting symmetry and recursive algorithms, we've recently been able to study systems of up to 6,144 pions. Okay. I'm not going to go into the details of how we did this, but you can look at a recent paper by Abbott last year. Okay. That's kind of extreme. But we can also think about a little bit, think about contractions in another way and make use of the fermionic nature of quark fields. And this can help. So let's think about trying to look at a nucleus. And this is clearly a place where the factorial growth of contractions makes things very difficult. So let's look at an interpolating operator n, labeled by quantum numbers q, and we're going to write this in some generic way. Um, as the following. So these A's, these are going to be multi-indexes, and they're spin, color, flavor, and space indices. Okay. Okay. So generically, an operator can be written as a product of field operators multiplied by some complex number weights. So because the fermions are antisymmetric, if I change the order of these fermion fields, then I pick up the appropriate minus signs. So I can always write this operator as the following, in terms of kind of classes of contractions. Um, so we've written this in terms of the n-dimensional totally antisymmetric tensor. And this is really a sum over all permutations with the appropriate sign of the ordering of the quark fields. And the weights are now labeled by an index k associated with a particular ordering A1, an ordering A1 through AN. Okay. So now a correlation function here so n q n bar prime q. Let's write this before we do the fermion integrations. And let's give ourselves a bit more space. Sum over k and k prime w a 1 prime w. If I've got all the indices right, I think that's right. So then we do the fermionic integration. Um, So we get the fermion determinant and things, which I'll just define the effective action depending on the gluons. And then I have the following. I can write this is K prime, W star, W. And now you can use the anti-symmetry to write this piece, well, after you do the Wick contractions, be many different combinations we can do, we can actually write this thing as the determinant of an object G that depend on the gauge field. So this thing has matrix elements Ij, which are built from the quark propagator. A, J, I, which is really something where we take the full quark propagator and choose certain rows and columns of it, and then take determinants. So you can see that on a given gauge configuration, evaluation of this correlation function here means really take a sum over many weight factors times determinants of matrices. And these matrices of size of the number of up quarks or the number of down quarks, the number of strange quarks. So the cost here goes like the number of weights, number of weight primes, which may be different depending if your operators are different. And then you can actually evaluate this in nu cubed plus nd cubed plus ns cubed operations. And that is because we can evaluate determinants using LU decomposition. Okay, and this is typically much less than nu factorial, nd factorial, and s factorial. Although, of course, the number of weights can grow quite rapidly. Okay, so let's say we've constructed our Wick contractions and we want to evaluate them. So a given Wick contraction it can be written in the following form. It's basically a sum over many indices, I1, In, and then let's do some J's. There's some tensor that depends on these indices. And then there are quark propagators. And after reordering the indices, I can write it in the following form. Okay. So this tensor contraction, you need to take a lot of care as to the order in which you evaluate this. Because this can dramatically affect the memory required and the computations amount of computation you have to do. So let me just give an example. Let's think about a system, fairly complicated. Two delta pluses, delta plus pluses, and two pi naughts. Okay. So let's think about memory that's used. So I'm going to write down a Wick contraction that comes from this. Okay. So let me do this. Okay, so this is going to be a delta plus plus, a delta plus plus, a pi 0, a pi 0. Okay, so one of the Wick contractions that we get here is going to look like the following. Okay, so you think about this, this is what we want. And let me take a copy of this. Okay, so let's think about evaluating these many sums that are involved in this. Okay, so I'm going to do it in the following order. I'm going to start from this point and go from here to there, then decide to do the sums here, here, 5, 6, 7, 8. Okay, so the order tells me what step in the summation, what step in the procedure I'm going to do the sums that are occurring at those sites. So a step. And what I want to think about is the number of free indices on the object I'm building. Okay, so at step 1, where's 1? Here. I take this object, and this has 3 free indices on it. Okay. At step 2, I contract that object with this one, meaning I do the sum corresponding to this line. But now I have, so I've got this and this, I've got 3 lines going out like this. So I've now got a 4-index object. If you think through this, if I then go to 3, then although that line gets eaten, I now have 2 additional lines. So I now have 5 external legs. Step 4, I have 4. Step 5, I have 2, 6, 2, 7, 2, and 8. I end up with 0. Okay. So somewhere in there, I need a temporary object that has 5 indices on it. Okay. And if the index space is large, well, that becomes computationally challenging to deal with. So let's instead do a different order of the contraction. And we'll go from 1 here to 2 there, to 3 there, to 4 here, 5 there, 6, 7, 8. Okay, and so again, step 1, 2, 3, 4, 5, 6, 7, 8. If you go through and evaluate this, you see that at step 1 I have 3. Step 2, I accumulate this vertex, but that has one ingoing, one outgoing, so I still have 3. Then I have 2, then 3, then 2, then 2, then 2, then 0. So I've managed to do the calculation in only using a 3-index intermediate object. Okay, so you can see that order we do this clearly affects how much memory we need. The other thing it can things that can be influenced is the amount of work needed. And there is, in fact, redundant work. And you might want to try and eliminate that. So let's look at these things up a bit. These are the same diagram. And if you count the work required here, if you just go around the diagram and do all of the summations, there are 20 summations that need to be made. There. So not specifying everything too carefully, if you look at this, you can see you can write it as some tensor with two indices, followed by a propagator with two indices, tensor with two indices. Whoops. So what I'm really doing is starting here, going like this, and so on. So let me just write this out. T3, 4, another propagator, 5. Now we get to a 3-index tensor, another propagator, another 3-index tensor, 8, 9, 10, S9, 11, another baryon, S13, 14, T14, 15, S15, 16, S9, 16. Ooh, that can't be right. 9. It's 912, I think. Should check that. S 617 T 16 17 18 S 18 19 T 19 20 S 21. Okay, so that's the work you need to do this, is those 20 sums. Now, if we look at this expression, we can see that there are actually common pieces to it. So for example, this blob here and this blob here are both kind of the same. They both have the same flavor structure. They're all U quarks because we chose these delta pluses. And they have all 3 incoming legs. Okay. Similarly, that blob and that blob and this blob are all the same. Okay. So I can do the following. We can pre-compute what I'll call B14, which is this object, which is really a propagator 1, 2, a T, 2, 3, and an S, 3, 4. Okay. And there's 2 sums here, so this was rank squared to make this object. Okay. Then I can look at B145, which is the other one, which is going to be a T123, an S24, an S35. And that's rank cubed. Once I've done that, the work required is in fact much less. It's rank to the 10. Okay, because I can write the whole expression now as T12 B23 where am I going? T345 T678 B19 ah, B six, 10, B1047, and then one more B. I've lost the indices. Sorry, let me pause this and check. Sorry, I just had to check that offline. So the last bit here is B958, and you can see the evaluation is just, I've gone through them carefully up here. And so there are now 10 sums that you need to do in order to evaluate this thing. Okay. So obviously this can get fairly complicated, and there's a lot of graph theoretic methods that you might think about in this problem to make it manageable. Okay, so that brings us to a summary of this module. So spectroscopy is a powerful tool for understanding QCD and learning about the bound states and resonances of nuclei. I hope I've told you that there are many different ways you can build correlation functions. To access the spectrum. There are many ways to extract energies from those correlation functions. Um, and I stress here these are energy bounds always. And you need to be very careful about the statements you make for those. So the computational costs typically increase the number of hadrons that are involved. And so that makes getting to nuclei is a big challenge. I think this is a field where there's lots of room for innovation. and also lots of room to impact phenomenology. And with that, I come to the end, and thanks for listening.